This talk is about, as you can see here, we have placed a lot of devices, so we'll try to explain everything in a moment, but in summary, we are going to talk a different approach on how to bypass the secure boot on a specific Qualcomm SoC. In this case, we are going to present how can we try to achieve this goal without knowing anything about the software is running inside the SoC, anything about how the secure boot has been implemented, or any particular if instruction we want to skip or something like that. This is the reason we named Blind Glitch, because we are blind, we don't know anything, and we are trying to bypass this. So I'll start talking about us. So my name is Hector Marco. I am the founder of Cyber Intelligence. It's a company based in Spain, and my colleague is Vicente Arnau. He's a hardware security researcher. So we have been working in smartphone security for a while. I've been working in cyber security for more than 15 years right now. And as I say, we are working in both software and hardware security at the company. So today we are going to talk just about hardware, but we are also doing software stuff. So right now we are working in a project. This project is basically named the EXFILES Project. So in this project, one of the main goals is to be able to access to data stored in modern smartphones. So as you can imagine, so right now it's not an easy task because everything is encrypted. We have the trusted zone. We have a lot of crypto devices. So one of the main goals is be able to access to this data in order to provide these critical evidences in criminal cases, right? So we want somehow to access to that evidences. So the main goals is find ways. So we need to find ways. At the same time, we need strong security for users, but we also need to provide mechanisms to access to this data, okay, especially in order to solve criminal cases. So as you can imagine, we have software and hardware approaches for that. So in this talk, we are going to just talk about hardware methods, okay? And basically, we are going to create and develop tools to improve reverse engineering. Means that we are going to try to go beyond the state of the art in order to provide the latest method and technologies in order to be able to retrieve data for these encrypted smartphones. So about this talk, so the main goals, as I say, is bypass the secure boot. All right. In real hardwares, BFU, which means before the first usage, which means you have the smartphone, something like that, and then you just need to press the power button, and this is the only thing you have. You don't have the code running, you don't have privileges, you cannot inject anything. We are assuming that we don't have any vulnerability, or at least we don't know any vulnerability, so we are blind. So how can we approach that? So the second main goal is not only bypassing the secure boot, we need to have the smartphone in a stable way. So we want to run code with maximum privileges. So it means EL3 in IRM. And why not? Let's try to provide a generic method. So we are blind, we cannot run any code, we want maximum privileges, and on top of that, we would like this method to be applied to other smartphones or other devices. So why not? So to start with, we just pick this device under test, which is the one we have in here. In the table, we have 3 of them. One of them is already running. Vicente will explain a minute later on about that. So this is the DragonBoard. Basically, we started with a development board because we didn't want to start with a super hard stuff. We just started with DragonBoard for DC, which uses the MSM8916 SoC. This is the one you can see on the screen. All right? So as you can imagine, the DragonBoard is using the Qualcomm secure boot. It's following let's say, that standard. So this board comes with the secure boot disabled. So this could seem strange to you, but don't worry. I'll explain in a minute. So one thing you don't need to confuse is that we have 2 main things. We have the secure boot, and we have the hash verification. It means that if you try, because I have heard about many guys working in different industry, cars, and so on, that they are just dumping the firmware, modifying a couple of bits, loading the firmware again, and then running it, and then you will get errors. Why? Because this is the secure boot. Sometimes this is not the real reason. Sometimes it's because there is a hash verification. So you need to at least know how this hash and secure boot works, at least a high level, okay? So this is what I'm saying here, right? So modifying the bootloader or modifying any code in the firmware will result in a fail, not because of the secure boot, but because it has, at least in this board. So the first thing we did was enable the secure boot, right? So that means that we have the keys, means that we can create our own firmware and then run it in the board, right? But this is just for the initial steps, right? So the final goal is we will be blind, we will have zero information about what is going there. So we are not going to use anything in order to bypass the secure boot later on, okay? So if we want to bypass secure boot of this kind of devices, right? So first we need to know in which point, because you can do it at different levels. You can do it when the system is fully running. You can try to glitch an application, glitch the kernel, glitch the monitor, glitch whatever, right? So we think, and we'll explain in a minute, that in some cases, the earlier the better, so we aim to bypass during the boot process. So even in that point, even if you are looking for to bypass the secure boot when the system is booting, when your smartphone is booting, and this makes sense because remember, we are in the BFU, before first usage, mean that we have the smartphone, but the smartphone is completely off, so you don't know the pin, you don't know the pattern, you cannot attack once the kernel or the full application of the device has been unlocked. So our aim is to bypass it during the boot process, right? So I'll explain in a minute what means PBL, SBL, and EDL. Maybe some of you already know, but just to ensure that we are all in the same page. So the primary bootloader is the first thing you will execute when you press the power on in your smartphone, also named or known as bootrom, probably you know. So it is the first code to be executed in the smartphone. So the second is the secondary bootloader. I'll explain that in a minute. So which is in charge of what next layers, next stages. But there is an important mode, which is EDL, which is emergency download mode, that basically is the one that if something happens, let's suppose that you are trying to repair your smartphone and then you remove the flash or the eMMC or UFS, what will happen in that case? Or probably you have seen a lot of people trying to reflash devices when your smartphone even doesn't boot, right? So the idea is there is an emergency mode that in case you have your flash or your flash partitions super damaged or whatever, you can always have some communication with the device. This is the emergency download mode. I'll explain in a minute. Okay? So this emergency download mode can basically, you can just connect a USB cable to your smartphone, so you can just remove the flash, then you can just press the power button, and then what you will see is that the phone is in a different state. So from that point on, you can talk via USB to that phone, right? Even if you don't have flash. So this code is inside the PBL, and this is called the emergency download mode. So in that point, you can actually send programmers send stuff to the smartphone, and the smartphone will load this code, but if this code is actually signed. So that's the challenge, right? So we will see in a minute. This is useful when partitions are corrupted, so this is what I say. And the good thing is that for this board, in that mode, as you can expect, it's running with maximum privileges. It means that you should be able to reflash all partitions, right? You should be able to do whatever you want. But as you can imagine, this has been only allowed for Qualcomm stuff. So that means that either you have an image verification, you have an image with the proper signature, with the proper stuff. So otherwise, the EDL will reject that, right? So you can send me whatever you want, but you need to sign this kind of stuff you are sending me to me. So our attack, I'll explain in a minute, bypasses exactly that. So let's put the smartphone in a strange state. Or let's try to force an error. Then we'll go to the emergency download mode. And then in that point, we will send some code to be executed. Right? The smartphone will try to verify that. If we manage to do the glitch exactly in the point that is doing this verification, then we should be able to run arbitrary code with maximum privileges, right? Again, the attack doesn't depend on flash partition. So I don't care Android version, I don't care about the bootloader version, I don't care about anything. You just need to tell me which is the SoC you are using in your phone, and this attack will be reproducible among all other devices using that. So I don't care about any version, about anything like that. So just to refresh you guys, so we have in modern smartphone, we have the secure world and we have the normal world. Remember in here in the normal world is when we are running Android and all the stuff, and this is running in background, let's say that. So what happened is that when you press the power on button, so the first thing is the first code to be executed is the bootrom. You already know that. We also know as PBL, primary bootloader. Okay. So the next steps are to load the secure SBL. We are still in the secure world, right? So this code is also, let's say, trustworthy for us. Okay, and from that point, the next step is load the non-secure SBL and also all the stuff related with trusted zone. Trusted operating system, trusted libraries, trusted applications, okay, the communication, the monitor, all the stuff involved in the trusted zone that you probably know. So we don't care about that, but just to let you know, this is in the normal world. And as you can see also, all of this stuff is in the flash memory, right? And all this stuff is in the ROM. So that's interesting for us, because if we can manage to try to fail or produce an error or to force to enter the phone in this emergency download mode, means that we are still in ROM, right? So that means that you will be able to somehow be in the maximum privileges in a mode that doesn't depend on the file system, on the version of Android, on anything like that, okay? So that's the idea. That's the main idea. So remember, when we are in EDL mode, so the next step is through USB, you can send a programmer, right? But this programmer must be signed by Qualcomm, right? And from that point, this is like a loop waiting for commands. So you can actually talk to this programmer you have just sent through via USB. That's the main idea, right? So power on, force an error, send a programmer, wait for commands. The problem is if you use a leaked signed programmer on the internet, you will be very restricted about the things you can do. You will not be able to down memory, you will not be able to write any random memory or something like that. That means that it's not useful for us. Because our main idea is let's try to run code in that place, right? So we can, for example, dump the PBL, the bootrom, right? So that will be the first step towards not being blind, let's say that. Okay, that's the main idea. So this is exactly the point we are trying to glitch, right? We want to bypass this signature verification. Again, the attack doesn't depend on the flash partitions. So the first question we did ourselves is, all right, so how it works, this verification? So I'll explain in a minute. So this is how it looks, the programmer we are sending through the USB. So basically, it's a regular ELF with a special segment, let's say that. In this special segment, you'll see that there is a hash table header, a couple of hashes, a signature, and also a couple of certificates. Summarizing, all these hashes are to ensure that those parts aren't touched. So if you change one single bit here, means that this hash will be different, right? If this is completely different, this will be a mismatch. Or if you keep that hash, the signature will fail. So basically, this is how the secure boot has been implemented, or how the signature verification has been implemented, right? So if we expand this signature, the certificate stuff, we will see 3 certificates. So the good news is that the bottom one is only checked against the root key hash. There is no decryption plus, let's say, basically, we are not verifying this root certificate as we are doing in those steps. Because here, what is basically burned in the fuses here is just a hash, right? So basically, we are getting the hash value of this certificate and then comparing it against the hash that has been burned in the fuses of the board, right? So it looks like they're similar, but it is not. Because in that case, basically, what you want to do is you want to decrypt and compare the hash with the verification, the classical verification operation. But in that case, it's only just a comparison. So it looks easier to try to bypass this than try to bypass the other. So we have, as I say, multiple opportunities. One is the one I just mentioned, but we could also try to bypass this step. Means that you can change this and this and this, right? You can change from here to apps. But at the end of the day, if you do that, you need to keep that or you will fail. So in summarizing, you will have a lot of places when you can glitch and you can bypass. Okay, but which one we should choose? As I say, it's much more, or it simplifies the attack if you choose the first one. And I'll explain in a minute why when we see the power traces, okay? So why this simplifies the attack? Why is better to do that? Well, I'll explain in a minute, but as I said, the goal is bypass the first verification. So just to refresh you about what we are talking about, how we obtain this code in order to do the reverse engineering, in order to know that it's better to do this first attempt, or we didn't. So we don't know, right? So we are blind, and we don't know what we are glitching, right? That's the point. So and then how do you know where you should glitch if you don't have the code and you cannot display, okay, this is the if. In here is doing the hash comparison. I want to glitch in here. So this is what you will find everywhere. So do the glitch here. We don't know. We don't have the code. If we have the code, we don't need to do that, right? But we can guess a probably timing area. We can guess, okay, more or less should be around this area. So that's our approach, also in a minute. Okay, and how can we determine this is the area? Well, there is an easy trick that we find that basically we can just send two programmers. One with a valid root key, means that this is the original one, signed by Qualcomm, which have limited capabilities, is not useful for us, but you can just send it, right? You will get a success, let's say that, right? But if you just slightly modify the programmer with a wrong key, then this programmer will be rejected. But this will leave some power traces. That's the point, right? So in here, we will see on the left a power trace when we are sending a valid programmer, okay, to the EDL with a valid root key. Nothing happens. But on the right, we'll see that the same power trace when trying to load a programmer with a wrong key. Let's say that. So what do we expect from here? Well, you can just look at this. We don't know exactly where, but we can say that it will be around here. Because otherwise, we will see more power trace. Right, okay. We don't know where, we didn't see the code. We know this more or less around this area, right? So I'll show you this full attack overview, and later on, Vicente will give you a more precise details about the equipment we have used, and we will do a real demo about what we are presenting here today. So we have our computer. Okay, we have also a USB sniffer, which is we are using the Beagle, but you can use different stuff. We have the glitch generator. Okay, we are using Chisper Nano, but this is something we'll explain later on. And we have a power supply, which basically is powering the board. Okay, so the first step is send a crafter programmer. So it means that you can download the programmer from Qualcomm, right? You can add the code you want, the perfect for you, with pick and poke, read, write, whatever, execute instruction, whatever you want to do. And then you are going to send this programmer to the board, but we'll go through the USB sniffer, right, until reach the board. But we will detect when this programmer is going through the wire. And when we see this programmer going through the wire, what we're going to do is to do this glitch. We will do a sort of the BDD in the board, right? So basically, we are going to send the programmer and trying to predict this area I showed you before, and then reduce the voltage. We are powering the board, right? If we fail, we just need to try again. We will cut the power, and we will restore the power, and we will try again. Okay? That's the main idea. So now Vicente is going to explain you the equipment we use, and we'll do the real demo in here. Thank you.
Okay, so thank you very much, Hector. Okay, so as Hector explained earlier, we have the PC, that's our main control. Then our FPGA, the one we're going to use to actually glitch the device, is the chip whisperer Nano. This is obviously controlled thanks to our PC, but it's going to be triggered by our USB sniffer. In this case, is the Beagle. And the way we reset the board is thanks to a relay. That relay is connected to the power supply of the board. And with our PC, what we're going to do is activate the relay, cut power, and then restart the board. Very simple. Obviously, our device under test is the DragonBoard, as we have been talking. So the first step is activating secure boot, because it comes disabled by default. Thankfully, Qualcomm has tools in order to activate secure boot. You can find them in the development section of their web. It's weirdly under the Windows 10 IoT Core section, but there you will find SecTools, which is the set of tools used to activate secure boot. It's in Python, and there are some bash scripts, so you can run it on Linux. And the customization guide is the actual PDF with instructions to activate secure boot in your board. So with that out of the way, we have to first generate our own keys. Those are the keys that we are going to burn into the SoC. And we also have to take into account that in these devices, the serial number of them is different to the one that Qualcomm usually expects. So we have to modify several files. In this case, here is the number we have to take into account when activating secure boot. Because else you are going to have some problems while loading your own programmer or activating secure boot in general. So once we have secure boot activated, we are going to actually touch the device. Why? We need a way to access that power rail. We need a way to affect that core. And for that reason, we need a clear line, a clear area inside that lane. For that, what we're going to do is remove capacitors from that same lane. In order to expose that rail, what we're going to do is remove C228. The reason why we remove this capacitor is it's convoluted. It's quite, there has been a lot of research behind, a lot of time, but we only removing this one, we managed to affect the device. If you want, we can explain later. If you have any questions, you can come to us and we'll explain in a little more detail later if you want. So once we have that removed, as you will see there in the left-hand side of your screen, that's more or less the schematics of the capacitors. That's with the capacitor removed. And the upper pad is the one connected to the APC rail. As you can see, that's the same capacitor. We soldered a copper wire that goes straight to the chip whisperer. And that's the one doing our glitches, as we explained before. So let's go to a very important step that is trying to characterize the device, try to learn what's the best glitching parameters in order to affect the device properly. In this case, if we insert a very long pulse, if we short the line for a very long time, we will get a restart. The board is going to reboot, but we don't know the state of that board. It can crash or it can reboot fully. Nevertheless, if we are very short with our timing, we might not affect the device. So the objective is to find a nice spot, an optimum spot, in where we can affect the normal behavior of the device, but do not crash it or otherwise affect the continuity, the normal activity of the board. So we activate the secure boot. So we have the keys in this step is quite fairly easy. We can build our own programmer. We are going to see in a minute what we did to characterize this board. So with the keys that we activate a secret boot, we can load them in, we can assign, the programmer, load that programmer in the board. And in this case, we modified a function. It's called firmware write. Firmware write is not used in the programmer. Well, it is used, but it's only invoked when you send that command via the USB. So it's untouched, so we can use it whenever we want. In this case, what we did was take the normal programmer. We put our characterization code inside one of the segments. And then we resigned everything thanks to the Qualcomm provided tools. This is the actual code of the code that we modified. There we have the modified function, is firmware write. In order to trigger a little bit better, we had a trigger high in order to see where our loop is happening. In this case, the loop is it's a double nested loop. We want a really big area in order to try to inject glitches in there to see if we are affecting the device or not. That big area is surrounded by a trigger high and trigger low, so we can see where that's happening. And then we return two strings via USB. If the value is expected, we return unexpected. But if something happened, if the value that we are trying to compute, if the value that we are expecting is not there or is different, that would mean that somehow we affected the device, so we are going to return a success. This would be the power trace of the whole operation. You can see it clearly here, but here we will have the lowering of the trigger, and here we will have the rising of the trigger. In this case, there's the rising edge, and there's the other edge. So we can see clearly that this is our region. So we are going to try to inject a glitch in that region, taking into account these timings. So what happens? Characterization made our lives easier in order to advance. But okay. We are going to face devices where we do not have the keys. We will not be able to characterize the device because we do not have the keys. All this talk, our main objective is to approach a device without the keys. Characterization is still doable. It will depend on the device and the different triggers and characteristics of the device, but it's still doable. In this case, we took this approach in order to better explain what we did and how we did it, and to help us know the best parameters for this device. But now that we know the best glitching parameters, and it's time to focus on the real stuff. In this case, and as we explained, we do not have the keys of the device. We would not have the keys of the device, so we cannot run this characterization step. But we can we can have the best parameters, and we can modify a programmer as we did in order to load and run all the attack. So in this case, our main goal is to glitch the EDL when, as Hector explained, when it's verifying this root certificate. So we have a couple steps. First is getting timing right. As Hector explained, we already see where the programmer is going through the wire, so we can trigger on that. But we also know more or less where the root key hash verification is happening. So we have a very clear window on where to start applying our glitches. So as we have seen, we already more or less know where that's happening. If we take into account that we can see what's happening through the USB wire, we can set a clearly defined glitching area. So there we go to the next step of our bypassing attempts. In this case, we are modifying this programmer. This is the same function that we modified earlier. In this case, we just want to see if we are able to run code. So we are just trying to print via USB a simple string. In this case, cyber intelligence 2022, we are executing code. So the main idea, as we explained, is to generate new keys. In this case, these keys are different to the ones that are burned into the device. They will make the device reject our programmer, but that's what we are trained to bypass. In this case, if we put everything together, we know, thanks to the characterization step, we will know the best parameters to glitch. We also know the best timing window in order to apply our glitches, and we have our modified programmer, so it's time to start glitching. Glitching has both advantages and some challenges. The way the USB stack works on the device, we still don't know that because it's a black box. So we have jitter in there. We don't know what the timings of that process of this packet. So our time anchors are not precise, and furthermore, we also not every glitch injected will be a success. So there's a little bit of randomness to it. So we have to try several times in order to first achieve a success. But in this case, we can apply a generic methodology to the devices once we know these parameters. And in this case, we will not have the need to reverse engineer to try to find code or leaks for our devices, because we can do this via power traces or inferring some information, as we said. So if you remember correctly from the first slides, this will be two of our main objectives, and we are going to see if we manage them successfully. Here is the results of our experiments. In this case, we left this run 125 times in 15 hours, and the average time that we achieved to bypass the secure boot is 7.25 minutes. We have a couple of layers. In fact, we had some serious ones of some 90 minutes without success, some 50-something minutes without success, but generally the timing window that we're expecting is between a minute and maybe 10 or 15 minutes. Here we have another plot that will help you see where the average time is located. So now we are going to try to see. I'm hearing the relay still triggering, so maybe it's possible that we do not have a success, which is weird, because thankfully we have a video, and you will see that in the video the success is achieved quite rapidly. In this case, we are going to check, but yeah, this is still running, so we are going to cancel this. Well, in fact, we are going to try and keep it running and see if eventually we get something. But basically, the demo of the video is the same as we explained. We run our script. Our script keeps running this loop. It's not the best quality, but it works. I hope you can see this. So here we see it's running. The video is barely 2 minutes long. So we are going to advance this. It's running, and there, sorry, we get one of our successes. You will see that in the screen in a minute. Appears the success time 1.5 minutes. It's 1.6, sorry, minutes. It's quite nice. It's a very nice timing. So we can know that the programmer is loaded. We can start sending other commands. In this case, our modify command is firmware write, as we mentioned. And if eventually we can see how in here how let me move the camera, how we are executing code with that string that we mentioned earlier. So, Hector, if you want to...
Yeah, to conclude, basically the conclusion, we have 1 minute time. So we really think that voltage glitching is a powerful technique. So this technique that we have presented today is not the glitch in itself. It's a combination of stuff. It's like an approach, a technique, a methodology. So in this methodology, we do not require the PVL. We don't need to know the ROM. We just need to send a programmer with valid and root key, so we will see those differences. So we will get the probability area. So we don't need to know how secure boot is implemented. We need to know the design, right? Because I showed you the verification stuff, but I didn't look at the code, right? I don't know today if there is a if condition. I don't know. Maybe the first certificate is. I don't know. I have no idea how the implementation has been done. I just need to know high level the Qualcomm documentation about. Okay, there is an L file. This is this verification. Super high level. I don't need to have the code, right? So we successfully bypassed the secure boot of this DragonBoard, right? So basically, as Vicente said, we just modify a Qualcomm signed programmer, and we just resign it with our keys, and then sign it to the board, and eventually we will get success. On average, 7.25 minutes, which is a very nice approach. We were happy when less than 1 hour, we are happy usually, so 7 minutes is super nice. So the important stuff, we also created a more advanced, it's not just a string, we also create a software, a PBL able to read and write memory. So we dumped the PBL, the bootroms. So this is a mechanism to basically dump bootroms. So you can use this approach if you want to do the bootroms. So we compared the PBL with the previous one when the secure boot was not enabled, and they were exactly the same. This is proving us that the attack is not only successful, but the board is stable enough to operate normally, right? So with the bootrom, so we are not blind anymore, which was one of the goals. So software vulnerability is the next step. So now that you have the bootrom, you can now apply all your techniques, your fuzzing, your every stuff you have in order to go beyond that. And then probably next time, you don't need to do this. You just need to exploit bootrom with universal vulnerabilities. But when you are blind, fully blind, this is an approach you can actually use. And that's all. If you have any question, we have 1 minute. Thank you.
Thank you.